Good evening, everyone. Am I audible? Good evening, everyone. Am I audible? Okay, let's wait for some minutes so that others can join. Then we'll start week 8 lecture today. Good evening, everyone. Am I audible?
Yes, you are audible, ma'am.
Okay, all right. So we'll start in just 2-3 minutes. Okay.
Yes, ma'am.
Okay, all right. So let's start today's session. So first of all, welcome you all in the week 8th for the course of Introduction to Machine Learning instructed by Professor Balaraman Ravindran Sir from IIT Madras. And in this week, we are going to cover uh, basically gradient boosting, random forest, naive Bayes and Bayesian network plus multiclass classification. So I got one feedback from the last week that you wanted to have some more information regarding ensemble methods, right? In the last session, we have majorly focused about the evaluation measures, and apart from those evaluation measures, we have discussed about ensemble methods, and in which two techniques, this is boosting and bagging, we are going to discuss today also. After this bagging boosting, we are going to discuss about naive Bayes classifier, or using a probabilistic approach we can use this classifier. So there are some assumptions that we will be discussing in naive Bayes, and we will be relaxing those assumptions in Bayesian network. So these two are related to each other, and these two topics will be discussed in the next week also. Means these things not, but related to these things. And last is the multiclass classification. So multiclass classification will be quite easy for you. So let's start with gradient boosting. So basically in the last session, we have started with ensemble method. So can anyone of you let me know that what is ensembling? Ensembling. Anyone?
It is to design multiple classifiers or multiple models basically, and then combine their results.
Yes, true. It's very true. So look, what the main objective behind this ensemble method is, all these predictions or all these algorithms or all these classifiers may or may not be correct, right? It's on the basis of your evaluation matrices. Secondly, it may be a random case that what data set you are choosing at which time, and that classifier is able to give you good results on that data. So question arises is whether this particular classifier and the data on which you are training, is it sufficient that you can have this model for real world? So this is a very big, question to answer, that whether it is good or not. So that's why we go towards this human approach. If you don't know anything, you take it in multiple iterations. For example, if you don't know about the answer of any question, what you do is you call some experts in that field, and from each expert you ask the same question, right? And after hearing their advice or hearing their answers, you can decide, okay, I can go towards this direction, right? So in the same way, ensemble methods work like this. So here we are going to discuss about two approaches, boosting and bagging. So basically I wanted look, there are not many, it's not possible for me to solve a question related to boosting and bagging, because it's a lengthy topic. So I am going to have some slides here, you can see that afterwards also, but I will be giving you some glimpse of it, how you can visualize that boosting or bagging can be done. Okay, because naive Bayes and Bayesian networks have many questions, and this topic may be confusing. So I wanted to give more time on naive Bayes and Bayesian. So if you have any doubts in boosting and bagging, please let me know at the same time. Okay. So first is boosting. So boosting means, as the name suggests, booster. It means that, let's say you have one classifier, you have some data. So this is the data, and you have one classifier. And obviously, if you are ensembling something, that's why if you have read the literature of this ensemble method, these are called as weak classifiers. Because obviously the particular classifier is weak, that's why we need more than one classifiers or more than one instances of the same classifier. So let's say this is your original data and you have applied some classifier. Let's say you have applied some simple method. This classifier can be as simple as average. Okay, so you have learned about regression, classification, SVM, discriminant analysis, decision tree. You have gone through with so many classifiers, but the model or the classifier can be as simple as that of a simple statistical mean. Okay, if let's say I have to take a prediction of in a regression manner, so what I can do, I can just take the average of the whole data. That can also give you some number. That won't be a good classifier or good regressor, but it can be a simple classifier like this also. Okay, so this classifier, we have applied this on this data and we got some results. So using those results, we have found that some of the data points are correctly classified. These are correct. And some are misclassified or these are incorrect. So it means that this classifier is not able to process the whole data at once. It has some mistakes. So what we can do is, okay, let me keep you for this type of data only this data, and I want to learn another classifier which can work on this. So I don't want to work on this, I wanted to work on residuals. Residuals means it's more like that, let's say I gave you some questions. Okay, I have some questions, just think it in a regression manner, you can be able to understand more correctly. Let's say I have give you 10 questions. Okay, and 10 questions are mathematical questions in which you have to answer in some number. Let's say I have given you some questions to add. Okay, a small kid is there and I have given some questions to add. So what he has given me some answers. Let us say out of 10 questions, 2 he has corrected, he has correctly answered, and 8 he has not correctly answered. So what he has answered, let's say the answer was 4 and he has given the answer as 3. So it means he is close to that 4 but not correct. So how much error it is making? He is making an error of 1. Okay. So what I wanted, I don't want another classifier to predict this as 4, but I want to predict another classifier which can predict it as 1, so that I can combine the output from all the classifiers and obviously can get the final results. So basically here this is called boosting, because when first classifier is applied, it is on the whole data. You give some weightage to these data points. Initially equal weightage is given to all the data points, and after that what data points are misclassified, the higher the weightage is given to them. And so as we have to calculate the next classifier which can predict this residual. So there are 2 types of boosting method that we are going to discuss here. First is ADA boost and second is gradient boost. So ADA boost and gradient boost both works in the same way, right? There is a small difference between the two. We will be seeing how they are going to calculate it. So basically, let us suppose this is the algorithm and you can have an idea. Let's say I have some training samples. Let's say I have 5 training samples, x1, x2, x3, x4 and x5. Okay, this one. Now, because at the initial of this experiment, I don't have any idea which are wrong, which are correct. I gave them the equal weightage, that is 1 by 5, 1 by 5, 1 by 5, 1 by 5. This is the weight I am giving to all the data points. So this is your weight. That's why it is written as the weight is 1 by n. Now for each iteration means this iteration, this is the first iteration, this is the second iteration, this is the third iteration and so on. Okay, so for each iteration, let's say I am learning a classifier. That classifier is h, this h. Okay, so at time t, at iteration t, we have another classifier. So let's say at iteration 1, yani t is equal to 1, I have some hx, that is 1. This is first classifier. It has given you some results. Okay, so you will be having some, you will have some y here. Okay, and you will have this y predict. So it means that this y predict. This y predict give you, obviously it will not be completely correct. It will be giving you some error. So you have to calculate that error. So you have to do 3 things. First, take the data, give the weightage to all the data points equally. You have y, yani output. Now calculate, take some classifier at iteration 1 and calculate the output simply. And when you calculate the output, you have to calculate the error also. So error, it means that y minus y cap, simple. Now what I wanted, I want to learn this weights. So I have as you can recall the linear regression, you have some weights and bias which you learn from this whole regression problem, but here there are another weights also, these weights you have to learn. So that's why a learning weight strategy is written here, and this learning weight strategy is going to be used as the higher the error is, more the weightage is given to the particular data point. Let's say, for example, x1 is the output of x1, actual output should be 4, and what your y cap is given as 1, so error is 3. This is error, this is your y cap, this is your y. Okay, for x2, let us say it is, the output is 10 and your y cap is giving you 9, so the error is 1. So these weights, so this error is more, that's why more weightage is given to this x1 rather than x2. Because why? It is very simple, as it is very intuitive, that we wanted the error to be low, right? So we want to focus on those points which are far away from the ground truth. So it is more like that ki, let's say ki I am giving you some questions to solve, and what I want to focus on that student who is not able to solve the question. Okay, those who are able to solve and have some minute error, I can say that ki, okay, I can handle this much error, but in my class I will pay attention to those students who are making more errors. Okay, so this is the actual intuition of this type of ADA boot system. Okay, so this weightage is more like the attention given to the student. Okay, so we have to update these weights also. After getting these weights, we go for iteration 2. So now the weightage is different. So it means like when I first came to your class, let's have this example, maybe you are able to understand more clearly. When I first entered your class, you all are same to me. Okay, so I have, let's say one lecture is gone and I have given you some questions. Obviously, every person has their own mechanism to learn, right? So let's say from that first test, I have some data points. It means I have some students who are actually giving more errors. So what I will do in the next week, I'll pay attention to them, right? So in the subsequent weeks, I try to give attention to those who are making more errors, and I will reduce my attention from them who are actually learning better. So let's say one student has more error in week 1 and it has some less error in week 2, so I'll adjust my attention right that. So this, in this way, ADA boost work. So is that clear to you? This ADA boost we have discussed, I have kept it in the last session also, but not able to discuss in this detail. So is that clear? The ADA boost, it means at each step it is boosting itself. Okay. So basically what losses are there, or these theoretical part, I think you are able to read it out from the PPT. So I'm not going to focus here, because today what I am predicting, that I wanted to have some questions from the assignments also, so that you can have an idea that how this probabilistic methods work, because we have some data topics for that also. So after ADA boost is more like, it's any classifier can work here. You are not restricting your classifier. You can have a simple regression method, simple linear regression for classifier 1, and another can be some another classifier, or the same classifier can work for it. But the gradient boosting comes after that, and it's a modern approach. Basically, it's after decision tree, because when we have learned about decision tree, the major advantage is they are interpretable, right? But they are prone to overfitting. Okay, so basically we are boosting with trees. So it's called as gradient boosting. So we are going to combine output from multiple trees and put it and take the combination out of it. I think I have given you some, okay, right. I have a problem solved problem with gradient boosting here. So just think about it. This is the same step. Boosting process is not going to be changed. So boosting is more like this see here, so this is your first iteration where your f1 is your first tree. Okay, so this first tree is basically, so this first tree is predicting something, so this y1 is your prediction, and now this is predicting, so this residual is going to be forwarded in the next step, right? So what we are going to do here is ki in the first tree, in the first step, this is the tree. In the second step we have two trees. In the third step we have three trees. So how they are combining the output, you are able to see that, let's say I have some x1 as okay, is it now good? Is it clear?
Ma'am, on your screen, there is some browser also.
Actually, I'm not able to see your messages then. So don't write in the chat box. You can just open your mic. I can just.
Madam, in call message, please. In call message is there, na? Please
Hmm.
click that one, madam.
Hello, Hanji. Yes, Gmeet screen is visible. I'm not able to. Then let's not write your messages in the chat. If you have any doubt, then please let me know. We can, by opening your mic, I can just.
Ma'am, if you are able to maximize the, yeah, fine.
Okay, so don't write in the chat box because now I'm not able to see your messages. All right.
Yeah,
So
sure,
just
ma'am. Sure,
oh,
ma'am.
okay, okay. So basically, what is boosting is in the first iteration we have one classifier, these three. Okay, so we will be having some output. So this output is, let's say, y1 cap. All right. Now in the second step we will have tree second. This is the second tree. This is your first tree in from the first step. This is your second tree. Okay, and this tree will going to predict the errors, not y. Just think about it. Okay, what I have let you know, this is your x, this is your y, and this is your error. Okay, let's say this is y cap also. So if iteration 1 is there, any I1, from I1 I will have x given to this classifier, some y will be given to this, and y cap will be predicted. From this y cap I calculate this error. Okay, in iteration 2, for iteration 2, your y is changed to e. It means you don't have to predict y in the second iteration, you have to predict error in the second iteration. So that's what I wanted to say is like that. Let's say just treat it like I have given you some questions, and those the answers of that questions are in numbers. So in the first week, if I am giving you that question, you are giving me some answers. In the second week, you don't have to predict the answers to me, you have to predict how much deviation from your last answer from the ground truth. Okay, so that I can have the total, total output from week 1 and week 2 with addition. So what, in the final end, what I wanted, we will be having, let's say this is your m step, so there will be m trees. So the output from first tree, output from second tree, output from mth tree will be added, and this will be your final output. So let's see some example. Okay, so you can have some more clarity about that. So here I have not taken gradient boosting for trees because it will be very difficult for me. So I have taken the classifier as simple mean. Okay, let's say the mean is the classifier. Okay, so suppose I am giving you a suppose situation, this is not the actual case, but I am not able to throw you some good calculation if I am going to use the trees, because it will have a lot of calculation. So this is your data. At the first time you have this data x and y, you have to predict y. So what you are going to do, let's say your first classifier is mean classifier. Mean means take the mean of this. So you have taken the mean of this, and the mean comes as 5. It's okay, no problem. So it means that the output of first is 5, the output of second is 5, the output of third is 5, the output of fourth is 5. So this is your output from your simple classifier at iteration 1. So this is iteration 1. Okay. Now what I have to do, I have to calculate error. So error is 2 minus 5, that is minus 3. 4 minus 5, it's minus 1. 6 minus 5, it's 1. 8 minus 5 is 3. So these are your errors. Okay. Now getting these errors, we call these errors as residuals. So this is a new term that you can say your errors or residuals. Okay. So basically this is your first iteration completed, and you have said that the weak classifier you have used here, the average is being used, is a weak learner, and I wanted to upgrade this learner with some more information. So what I wanted, I want another classifier. Okay, so that was H0, let's say, because generally we start with 0, that's why in machine learning or mathematics we start with 0. So these are your H0, this is your H0. Now H1 is, let's say some classifier is there. Imagine, because gradient boosting it is, let's say you have some decision trees. Okay, from those decision tree I make some, I learn for this output. It means now I don't want y to be predicted, I want in the second iteration this residual to be predicted. And just think about it, let's say the classifier is giving you minus 3, minus 1, 1 and 3. It means it is giving you all this. So it means now your residue, after getting this, the next residual 2 will be 0, because you have predicted all the residuals completely. Okay, so you have to go on this processing till the residuals are less. Okay, so how the final testing will be done? So it means that in 2 iterations I have completed my model. From the first I have this value 5, and from the second I have these residuals. So how will I test my system? Let's say this one. So basically we have a formula that this is your 0th classifier, this is your first classifier, this is second, until t. So here we have only 0 and 1. After that all the residuals are 0. So it means that for every x I'll pass it into this classifier and get some output. So obviously this classifier was, this regressor was of average, that's why it will be giving you 5. In the second one, we have to pass the input and get some value. So here I will get the error. Okay. So if you will see, like if we add these two things, we will get the final y. So it means that in gradient boosting, what you do, you go in sequence. You apply the classification, or your, generally it is used for regression purposes because it adds the output, it enhances the output. So what it do is, from the first classifier it gives you some output, from the second classifier it gives you some output, just combine those output together. So if it's regression, we generally go for addition, and generally because it is used for regression purposes, but if you are going to use for classification, we have no other way to go for the majority voting. Okay, yes, someone wants to ask. Any doubts here? So this is like gradient boosting, just that here we are having these classifiers as trees, not other classifiers. And trees or decision trees have their own advantages. So we are combining those trees, and we are working towards in the sequential manner. Is that clear to you? Yes or no?
So the weak learners are nothing but the initial models that we will be finally combining, right?
Yeah, right. These are why they are called weak in sequential learning, because the first learner at the 0th iteration, this one, is taking the full data. After that, you are taking the weighted data set, okay, where the misclassified data points are giving more weightage. So it means that it is not for the whole data, it is giving to the weightage where the error is more. So it means the combination of these weak classifier will give you the whole bunch. Okay. So it means it can be look like that ki, if a teacher is giving attention to a particular student who is weak in a particular week, but if the overall case in the whole session or in the whole course of 4 months or 6 months, we can have an idea ki those students have been given weightage in their particular week, and now as a whole they are all good to go. Okay. So this is basically your boosting methods.
Ma'am, is there any reason why we go for weak classifiers alone or not the stronger one?
Actually, think about is ki how can you say the classifier is weak or strong? Okay, so we have some situations. So where we can say that ki let's say we have some complex data. Ultimately, if I come towards that from the first definition, that we don't know the actual distribution of data. Maybe it has some complex distribution where, let us suppose like this, okay, this is the data. So this is the major distribution is here and some distribution is lying like this. Okay, so if you define some classifier, then obviously because majority of the distribution lying here, the classifier will be biased towards here, any classifier. Or if we start from here, because these are some random guesses, we start with some initial weights. So I can, or either we can bias towards in this region. Okay, it's a very a very simple case which I am telling you. So what I wanted ki why not I just randomly choose some classifiers and sequentially just fine tune them. So this is another way to go towards that. Generally we don't do this. Boosting is actually very expensive to do, ki first you have one learner, then take the errors, then apply another learner, then take the errors. It will have a lot of complex things. Presently using the deep learning models, generally we don't use boosting in this form in a raw manner. We can use boosting in intermediate layers. Okay, so another thing, when you will be reading some more advanced subjects of this AI machine learning, from my experience I can tell you that these are the terms, okay, which you should keep in mind ki, okay, these can be the actions taken if the scenario is like this. So it's not like that you have to follow it from scratch. If you have, let's say ki you are learning neural networks. Okay, so in neural networks you have some network like structure, right? So here in the between of these layers we can add these type of ensemble methods. We can combine multiple layers, we can combine multiple features. So this analogy of boosting is applied somewhere in between intermediately. We are not using it in a scratch thing. So these things, that's why, are also very important. We don't use these things in the scratch right now, but somehow we can go with these things in some intermediate forms to enhance our system. All right.
Ma'am, ma'am, what is the exact difference between ADA boost and gradient boost now, that equation wise?
Basically, ADA boost comes first. When boosting start, it was the first algorithm, ADA boost, with exponential loss. Okay, so here the important is the residue.
With the same example, could you just say how it is different, both the two things? There also we are boosting
No.
from the output of
Yes.
the first.
Yes, just
So,
think, just think about this. So this residue is different. We are calculating weights. Here weights are calculated, and the more weightage is given to the misclassifiers. And again the data is given to the next step with some another weights.
how do
So
we know
this
more weight is given to the misclassified? How, from here, how do we understand that more weight
just
is going to misclassified?
this is your error, right? So the weight is given to the classifier where misclassification happens. So this is the misclassification. So where the misclassification,
Okay.
right? So that's how the weightage is given to it. But in gradient boosting, this weightage is not the simple weightage. We are just having the residue, and we try to predict that residue. Here we are not predicting the residue, we are actually using these weights and then applying it to the system. Okay, so using these weights we are combining all the outputs. It means that it's more like that. In AdaBoost, the classifier 1 with alpha 1 weight, classifier 2 with alpha 2 weight, classifier 3 with alpha 3 weight, and add them at the end. Here we are in gradient boost, we are not using the explicit weights, okay? Because we are during learning, we are actually learning the residue only. So this is the basic difference.
No, so here also in gradient boost also that epsilon will be calculated, epsilon t.
Basically, epsilon t will be used for the weights only. It's used.
So
It's
there
used
we
in
are
the.
computing some residual. What is the equation for that residual?
Yeah, you can say like that. Ki we are using this residue to compute the weights. Not exactly we are predicting these weights.
No, actually, ma'am, one doubt. Actually, here we are using the errors to compute the weights. There we are using the residue. So residue and error, are they the same function or is it different?
What I mean to say is, here we are explicitly calculating these weights, but in gradient boost you will not find the weights, alphas, not written. So alphas are not written, you are just predicting the errors in the next classifier. There weightage is given to each data points in different forms. So basically while combining the output, those weights are going to be important role to play. Here these weights are not
Here it should be all
explicitly
equally
calculated.
weighted. Here it should
Yes,
all be
yes,
equally weighted.
yes, you can say that. So here the residue is directly from the mean square error, but here your residue is not mean square, it's exponential loss. Okay, so that's
What is
why.
the advantage of each? What is the advantage of mean squared over exponential loss?
So this is generally used for classification purposes, where the logarithmic is there.
We
You know,
use
we
exponential loss for classification and mean squared for regression. Huh?
did this, right, right.
So we use AdaBoost for classification and gradient
Yes,
for
it's
the
at the
descent
start.
for
Yes, at
okay.
starting, this AdaBoost is actually using this exponential loss. That's why we can say that some logistic regression purpose like thing is going on. But now you know that regression and classification are actually linked to each other. So you can somehow, apply some deviations there, and you can change from classification to regression easily. Important is the concept. So these two AdaBoosts and gradient descents are introduced in one by one. So at the starting, this AdaBoost gives us the information of boosting, but after that, because this getting those advantages from decision trees, we specifically using this decision trees here. So gradient boosting is specifically using decision trees generally. So that's why they are called as gradient boosted decision trees also. And
Okay.
another,
Can we say
yes,
that gradient boosting is better performed in many situations other than ADA boost?
yes, that's why it is popular also. Means
Okay.
getting, in many application, AdaBoost is not going to be performed well due to some convergence properties. Gradient boost works well. Secondly, these decision trees are very, useful because they were interpretable and they are more accurate from the traditional machine learning approaches. So
But this
basically,
is used for regression, gradient boosting, or it's used for regression and classification.
it can be used for classification, but you have to somehow, have a variant of it. Initially, it is with your errors and residuals, so it was used generally for regression purposes. Just think about it, ki what you want to do in classification. Okay, in classification you have to learn this what do you say, hyperplane, right? So let's say ki your optimal hyperplane is more like this. It's more like here. This is your optimal one, this one. and this is your predicted one. So how much deviation you have to push towards here? It's more like that. So that's why every machine learning algorithms can be used for either classification or regression, but you have to make some changes into that. Am I able to explain it or not? Means, just think about it, SVMs are actually built for classification purposes, but now we can use it for regression also. So ultimately, decision trees are specifically we have started with for classification, but we can use it for regression also. So you have to make some changes there. That's why learning is important. How the methods are learning each other, that's final optimization methods, what you are going to take. If you are going to take residuals, it is more likely to for a regression cause. If you are taking some probabilistic approach or this this Bayes approach, naive Bayes approach or Bayes approach, where you are having a maximum likelihood estimation, you are going towards the classification. It's a small difference between them. For me, it's actually a small difference. For calculation purposes, obviously, it's a big one. Okay.
So why is it saying that gradient boosting is more prone to overfitting?
Sorry?
Why gradient boosting is more prone to overfitting?
Because it is particularly using this decision trees, and decision trees are prone to overfitting.
Okay.
Okay. So gradient boosting, after gradient boosting, we'll learn about.
Okay.
All right, good to go.
Yes, ma'am.
Okay. So next is we will be discussing about random forest. Actually, from all these ensemble methods, this one is the most popular. It also uses decision tree actually. Okay, so there is a small difference between simple bagging and random forest. We'll discuss it somehow later. So first let's discuss what is bagging. So bagging is parallel process. So it's more like that I have some questions, and I have 3 students or 4 students. I have randomly divided some questions among them, okay, and I take the final output. So it's more like the majority voting type thing. So it means parallelly all the students are working on those questions. It may be that some question can be common to some students and some may not be. So it means like I have just randomly given some questions to 5 or 4 students, and after that the output from all those 4 or 5 students are combined at the end. So these are the parallel processing. So this bootstrap aggregating or bagging use the bootstrap technique. It means that it divides the question randomly with replacement. That's why I'm saying randomly I am associating some questions to every students. Okay, so that's why it is called bootstrap aggregating. At the end we are aggregating the output of all these classifiers, and initially we are giving them bootstrap data. So it is called bagging. It is generally used for the problems which have more variance. It means which are prone to overfitting. It means that let's say while let us suppose I have one student who is good at he has listened to the class very carefully, but he don't understand the concept, but he is able to get how can I just project it in a way? Okay, let's project it in a way that I have given you some revision questions in the class, and one of the student in the class is very attentive to hear each and every word what is he speaking, right? So he don't understand, but he is able to grasp what he has listened, so he remember all these things. So when I give some questions to answer, he is able to give me all the answers correctly, right? I can't say that about that student because I am giving you this information. That is not a generalized way of learning, all right? So if I am going to use that classifier as a classifier, then obviously in the real world that person is not able to grasp the problems and will answer it correctly. So what I will do, I'll take the average of the class. If I am saying that okay, the learner is just like that student, I am just going to represent that student on the behalf of the class. No, it's not a good idea. So what I wanted to do is, I will pick up randomly some 4-5 students, I'll give them some questions so that this overfitting situation will not happen, right? One classifier can be overfitted, other will not be at that much. So that's why it is generally this bagging techniques is generally used to reduce the variance. So if you are reducing the variance, it means the problem of overfitting is there. So that's why we are training the models multiple times parallelly. Okay, so it may be that first classifier or first instance maybe some overfitted data or overfitted model, but the others will not be like that. So that's why this bagging comes into picture. Question is there is any situation where we can say that okay, this situation will lead to reduction of variance more. What I mean is like that, let's say I am picking out some students randomly, okay, and those random students are similar to each other. It means they all are overfitted. So it means that we wanted the classifiers that are uncorrelated. So I want some, the predefined knowledge. I will pick those students who are very far from each other. Because what I wanted to say is, if you are sitting with some type of students, you have a same mindset. So it means that this bagging technique will work best when the base model or the classifiers or the weak classifiers are uncorrelated. It means they will not give you the same results. Then and only you can have this reduced variance thing. Because if all the classifiers are correlated, it means, let's say the classifier 1 output as yes, and it is correlated with classifier 4. So obviously it will also be saying it yes. So what is the need of introducing this classifier? It will not give you something. It will increase the error because it will increase one vote extra. And obviously they are correlated, so their answer will be correlated as well. Okay, so it means that we have to choose some models which should not be correlated. So for that they introduce this random forest. So what is the difference between simple bagging with decision tree and random forest is? One way is, let's go for the traditional way. So how the bagging appears, that there is some data 1, 2, 3, 4, 5. I pick some data and apply decision tree 1. Okay. So same data, I pick some data, I apply decision tree 2. From this data, I pick some data and apply decision tree 3. Okay. So after that we can combine it. This is the traditional approach. This is not called random forest. There is a small difference between random forest and this technique, that bagging is done, yes, but feature randomization is also there. It means that, let's say you have a data with 10 features. It means we have x1, x2 till x10, then y is given to you. Okay. Before this random forest, what I am doing like that, if we have these 10 attributes, we give all the attributes, but we just divide these data points. It means I just divide the students. Okay. Some questions which I have given to you, I have just divided the questions. It doesn't matter that what are the features of that questions. Okay. So now what I wanted to say is, in random forest, when I am dividing the data, let's say I have kept 10 let's say I have kept 100 samples. Okay, 100 samples from this data, but I have to choose some of the features. I will not choose all features. So let's say for this 100 data, I choose x1, x3 and x5 only and create a classifier. Again, 100 samples are chosen with x1, x2 and let us say x5, x6 or x8 also. So it means that now feature randomization is included in this random forest. Why it is included? To make the classifier uncorrelated, because They are using same classifier. It means here decision tree is used, here decision tree is used, here decision tree is used. So, but in this decision tree, I am just giving x1, x2, sorry, x1, x3 and x5. So, decision tree is based on these features only. In second one, I am giving only x1, x2, x6 and x8. On the basis of these features, this second decision is to be made. So it means that these D1 and D2 will be uncorrelated to each other. Maybe the features will not be common. It may or may not be. So that's why we are selecting some of the features and putting it in one classifier and some of the features in the other classifier. But I am not giving you explicit call that those two feature sets will be mutually exclusive. No, I'm not saying like that. It means this is also being done using bagging. Some replacement of features can be done. So this is how this bagging with decision trees plus feature randomization is called as random forest. Is that clear? That what is this random forest? So basically just you can have some this type of features. So x1 features is not just like it is x1, it means some x1 set of features, this is x2 set of features, this is x3 set of features, and there are these decision trees. So maybe some decision will be made and you have to take, for classification you have to take majority of voting, and for regression purposes you can take the average out of it. Is that clear? Yes or no?
Yes, ma'am.
Okay, so these are random forest, and this is also ensemble method, and it's easy to implement actually. Secondly, in boosting you can think about it sequentially. You are running the classifiers 1 2 3, okay, but here what you are taking is, let's say we have total 1000 features, okay, and I separate it into 10 10 10 features separately. So it's more like a feature reduction technique can also be used here. So you can have an idea that if features are correlated, these separate trees will be easy to run with rather than with all those 1000 features. So it means there are multiple advantages of this random forest. That's why it is more popular also. Okay, so this is the basic difference in the crux, you can say, for random forest, which is bagging, and this is gradient boosting, which is boosting. Both uses generally decision trees. Okay, so bagging is used to reduce variance, boosting is reduced to it introduced to reduce bias. So it means it is used for overfitting. It means if the data is overfitting or model is overfitting, use bagging, and if you are underfitting, so it means you can go for boosting. Okay, so other things are actually related, that here the trees are trained independently because these are parallel. This is obviously, here it is sequentially trained. Here the model works well with high variance model because it reduces the variance. If already the variance is low and you are going to use random forest, then what you will do, you will make the system underfit. Okay, and this model works with high bias because it reduces the bias in the system. As you can see that this is obviously computationally expensive, and it is good for large data set because it can reduce somehow the feature sets also. So these are the basic differences between boosting and random forest, or you can say that boosting or bagging. Okay, so till now the ensemble techniques are over. So basically in ensemble technique we are saying that if you have a problem of overfitting or you have a problem of underfitting, just combine some inputs and take the average or majority voting at the end, take the aggregated results at the end, and either using a sequential process or using some parallel process. So this is for about boosting and bagging. One stacking we have also discussed in the last class, which is somehow similar, which uses both of these, somehow you can say like that, because it is for aggregation, it is using some more learning technique, that which is to be chosen at the end. So it's more like that. So this is all about ensemble. If you have any question related to ensemble technique, then go for it. Good to go. Can we go further for the Bayesian classification? Yes or no?
Yes, ma'am.
Okay. So till now we have seen that as I have already discussed, there are two basic approaches that we have applied from week 2. When we learnt about regression, we uses residuals or errors, right? We reduce, optimize the mean square error, we minimize the mean square error and go towards the optimization. Second, if we have worked for classification, then obviously the error term is not a big thing in the picture. The probability is important. So here we have seen the maximum likelihood estimation. And there we have seen one formula in which what we have seen that the probability of, let's say, A given B, how to calculate it. So it's more like the probability of B given A into probability of A divided by probability of B. Okay, it's a simple formula. So this formula is also known as Bayesian formula, Bayes rule. Why? Because this thing, so this conditional thing is called as conditional probability, and Bayes theorem or Bayes rule is the first rule of probability which can estimate this conditional probabilities. So here we are using this Bayesian theorem for classification. So it's a probabilistic approach to classify using Bayes theorem, obviously, and this is the Bayes theorem, one of the Bayes theorem. It's a systematic way to calculate the probability. That's it. So there are multiple key advantages, but let's see some, questions. So first, what is Bayes theorem? So right now I have given to you the Bayes theorem. Here it is written. This. So ultimately, if I give you some tricks and tips for this, just think about it. In any probability which is in the conditional form, one is the given condition, this is your given condition, and this is to be calculated. Okay, so let's say I wanted to ask you that what is the probability what is the probability that a particular Mira is going to have umbrella if it rains tomorrow. So if it rains tomorrow, I have given you this condition. So what is the probability that she will be carrying the umbrella? So it's more like a conditional event, conditional probability. Or if I say that let's say in the two tosses, what is the probability the third toss outcome will be head if the two toss before that there are two tails. It means if there are two tails, then what is the probability here will be the head. Okay, so first we have to think about that given probability. It means that from the whole subset, now this was the whole subset, and if you are giving some condition, it means you are talking about the subset. So let's say this one. So now you have to take the probability, the outcome from this set, not the whole set. So this is what I wanted to say. In the given conditional probabilities, we have some event that already happened and we know it for sure. So from that happened event, now what is the probability? Okay. So there are some terms also that we have used. So first is we have to calculate this thing. Okay. So this is called posterior. Posterior means after having E, what is the probability of H? So it means posterior, after having E. So this is like probability of hypothesis H given evidence E, given E. So to calculate it, whenever I remember it, so there are two terms. First is numerator, second is denominator. So numerator is again one conditional probability terms comes here by opposing it. So in machine learning, generally what we wanted to know the weights given data. Data is given to you and we want to find weights. So we want to calculate the probability of weights given data. But in actually, when we have the data in our hand, okay, so having some initial weights, what is the probability of data can be easily computed. That's why we use this rule. दोबारा से सुनना, when we have data in machine learning, we wanted to calculate the weights, we wanted to calculate what are the parameters, but in using this Bayes theorem, we started with some parameters that are very raw, we have to fine tune it, but we have them in our hand. So having those initial parameters, what is the probability of the data can be easily computed. So that's why we can able to use this Bayes theorem very effectively. So this reciprocated probability term is called as likelihood, which is very important. That what is the likelihood? Why this likelihood terms comes into picture? Likelihood means those weights you are using is in the initial form. You have to fine tune it. So that's why this is called likelihood. It is very probable. It can be changed. Okay. Second term is used as here. Look, every time when you write like this, na, E by H, then the multiplication term will be the given term only. This always remember. Generally, we write it E here, don't write it E. If you are writing here given term, then product will be with the given term. Okay, so this is given, so product will be probability of H. And this probability of H is prior, called prior. It means it is likelihood, it is prior. Prior means which is given to you. That's why it is called prior. In numerator, what is left? E is left, so we will write as E. And this E is called as marginal probability, or you can call it as total probability. Okay, let me give you some more examples, some more intuitions out of it. So if I have asked you to calculate, this H by E. So here this probability term, this total probability term will be in the summation of something, and generally it is the summation of this over H. So it means there will be multiple subsets in this E which will be combined together, and it will give you the whole probability of E. But what I wanted to find that given H, what is the probability of E? Okay, so we will have some questions for it. So let's have some example. So suppose a person takes a medical test for a disease. So it means that there is a medical test and there is a disease. So it may be that disease can be present or not present. Medical tests say it is yes or no. So there are four things actually, whether the test is positive or disease present or not. Okay, so what I wanted to find out is if the test is positive, then what are the chances that the person is actually having the disease? So I have four outcomes here: disease and no disease. The person is having disease or no having disease. Second, because the test has been run, so whether the output of the test is positive or negative. Okay, so this is the probability that I want to find out. So according to the Bayes rule, write the Bayes rule. So using the Bayes rule, this is your disease given positive test, reciprocated. So I have written here positive test given disease multiplied by P of disease and divided by P of positive test. Okay, so I will be giving you some values, and you have to find out that what are the other values. So first thing that I wanted to know that what is the probability of these four terms. If I know all these four terms, maybe I am able to get some idea of this question which is to be asked. Okay, so first is these are given to you. So P of disease is given to you. This is given to you as 0.01. Likelihood positive test given disease, this is given to you 0.9. And one thing is given to you that positive test no disease is 0.05. Can you give me the probability of P of positive test? Anyone? Just think about it. and give me the answer for this thing first, that what is the probability, total probability of positive test. These are the three things given to you. From these three things you are able to calculate or estimate this positive test probability, and after that you are having the all three values and you will be able to get the probability of disease given positive test. So anyone? I'm giving you 2 minutes to think, and if someone has anything to say that how we can proceed with this, for this you can also open your mic. Is the question clear to you? Yes or no? It's a simple question that you have to find the probability of disease given positive test, and according to the Bayes rule you can expand the formula in this way.
Ma'am,
Ma'am,
I
yes?
wrote the answer in chat box.
Okay, let me see. .18. Let's see the answer is correct or not. Anyone other, any other who has tried, or any other person who has tried this? 0.18. Let's see. Give me 2 minutes. Maybe some others are also working for it. So probability of disease is given to you, likelihood of positive test given disease given to you, false positive rate, probability of positive test with no disease given to you. Then you have to find out this numerator P of positive test. Anyone else who are trying? Okay, can anyone let me know, someone has solved this 0.18 with, can anyone tell me that what will be the components that you need to calculate the probability of positive test? What you will need it?
Positive test, given disease, positive test, no disease.
So basically, let's start with this. Correct, very good. We have two options, okay, disease and no disease. So ultimately there are some probability of disease and no disease. So probability of disease is 0.01, then obviously the probability of no disease will be 1 minus 0.01. Okay. If the disease has happened, then there will be two cases, positive and negative. And here also there will be two cases, positive and negative. Okay. And I want to calculate this positive cases only. Alright, so if you use this type of hierarchical chart, you can have an idea first. The first thing is, what you will do, you are here. So let's say whenever you are going to use AND operation, means if I am saying it AND, then you will use multiply. And if I am telling you OR, then you will add. So you are at this position and I am saying you that what is the probability of positive test. So you will say, ma'am, we have two options. Either we can go with this branch or with this branch. So I am taking it as here OR. So it means the plus will be here. Okay, let's choose this branch first. So if I choose this branch, I have to go towards this disease. So what is the probability of disease? 0.01. 0.01. And then the probability of positive will be, it is given here, 0.9. Because these two are related to each other, that's why I have multiplied it. Another way will be no disease, that is 1 minus 0.01 multiplied by this positive case. This positive case is given to you as 0.05. So in this way you are able to solve this and you will get the answer finally like this. So it means the 0.18 you have given me the final answer, or this P of positive test who has written in the chat box?
P of positive.
P of positive will be 0.05. So the positive test will be P of disease into P of positive test given disease plus P of no disease multiplied by P of positive test given no disease. So whenever you are going to calculate it, it will be 0.0585. Just check it once more. So is that clear to you? Anyone having any doubt in this step?
Clear, ma'am.
Clear? Okay. So now you have all three terms. What you need this, you need this, and you need this. Okay. So you can easily use these three things and calculate the final probability. So it means that 0.9 into 0.01 divided by 0.0585, which is 0.154. It means there are only 15% chance that the person actually has the disease despite testing positive. So what you wanted to find it out? This. If the test is positive, then only the 15% chance of this medical test is the person is having disease. It means that this test is not very accurate. सिर्फ 15% चांस है कि वो आपको डिजीज बता रहा है पॉजिटिव होने के बाद. इट मीन्स बाकी बचे चांसेस में तो डिजीज होगी नहीं आपको, राइट? सो दिस इज हाउ दिस बेस थ्योरम इज वेरी इफेक्टिव. So it's a simple example of Bayes theorem. Now using this Bayes rule, we can develop a classifier. Okay, so how we can develop a classifier? Let's say we have some data, this x, okay, in which let's say it is x1, x2, x3, these are the features. So this is, मान लेते हैं, this is first point, second point, third point. Okay, this is your data, and you have some classes C1, C2, C3 and so on. So there are, let's say, 3 classes and 3 features. Okay, let's say 2 classes. It will be easy to give you an answer. Okay, so now what I wanted, using this Bayes rule, I wanted to find out that given the data, what is the probability of C1? Given this data, what is the probability of C2? So let's say what I want to find out, given data, what is the probability of C1? Given data, what is the probability of C2? So if let's say this is 0.8 and this is 0.1. So for this data point, for this first data point, I am talking about this first data point. So how will you classify it, class 1 or class 2? Let me give, just give me the example, answer. If for this data the probability of class 1 is 0.8 and the same data the probability of class 2 is 0.1, it should be 0.2 actually. So which class will you classify?
C1.
It's so intuitive, it's so present right in front of your eyes. So it means that we have to take the maximum out of it, right? So it means that using this Bayes rule, because this is the conditional rule, right? So using this conditional probabilities, we can use the Bayes rules and we can find the probability of each class for the particular data, and using those probabilities we can find the maximum out of it. So this is written as maximum class. So argmax means take the maximum class out of it. So this will be the class that will be the best classifier. So this is called Bayes optimal classifier. So what we generally do it for each and every data, we calculate the probability for each class, and the highest the probability is, the class is associated. Okay. But if you are going to calculate this type of probability for each class, then it will be very computationally expensive. Alright, because first we don't know the class distributions, we don't know the probability distribution. Here I have given you the probabilities, right? If you don't have the probability, we have the distributions, but we generally don't have it. So what to do? So there are another methods called naive Bayes or Bayesian networks comes into picture that can help you to somehow solve this problem. So here example is given to you. Let's say there are 3 classes A, B, C, which I have given you the same example. The probability of A given x 0.4, B given x 0.35, C given x 0.25. So which is the maximum? 0.4. So class A is chosen. So using this Bayes rule is so much important for classification purposes that we are going to see that how the variants or some algorithms use this knowledge. Okay, before that, uh, we have one classifier KNN, that is K nearest classifier. Have we discussed this KNN with you? I don't remember if I have discussed it with you or here in IIT.
No, ma'am.
No. So KNN is more like, let's say, you are sitting in a class, okay? So it has no training required. No training is required. So what I wanted to get is, just think about, I just enter in your class and I don't know any one of you. मुझे आप में से कोई नहीं पता, okay? Now a student comes into the class and he just come and sit with the people at the back, and those person are making noise. So it means that my first human intuition, because I don't know anything, I'll think like that कि this person is maybe the friend of them and he is more similar to them. So that's why its name is more like K nearest neighbor. So what I am going to see like that, here we don't make any discrimination boundary or decision boundary. We have some data, okay. Let's say this is data from class 1. This is data from class 2. There are some here, okay, some, let's say here. So and I want to check about this point here. So what I will do, I will find out the K nearest neighbor. If I am saying 5 nearest neighbor, then you will choose out the neighbors to the particular data point, and I am going to find out 5 nearest neighbor. If you are going to say 7 nearest neighbor, means the value of K is equal to the number of neighbors. I find out that how many neighbors are around it, and I just check the label of them. So I am not going to check the label of any other data point. I am just going to just search locally. So if I want to find out about a particular data point, I will not go towards whole data, I will just focus on the nearest neighbor. So nearest neighbor finding is very easy, but it is very computationally expensive. How you will find the nearest neighbor if you know about the whole data set, right? So let's say ki if I want to find out where a particular student is sitting, right, the nearest one from that a particular student, I should have the information that how much expansion of this room is, right? So that's why we have to first find out the nearest neighbor. So let's say ki its nearest neighbor, 5 nearest neighbor is x1, x2, x3, x4 and x5, and x1 belongs to class A, x2 belongs to class A, x3 belongs to class A, x4 and x5 belongs to class B. So I take the majority. So I will give this data point label as class A because majority of the data set around it belongs to class A. So this is more like the Bayes probability. It's also like the Bayes rule that the higher the points from the same class is surrounding you, it means you will also have the same label. Okay, this is called K nearest. Is that clear to you? So it's more like, it's also like the probability that how much data of the same class surrounds you. Okay, all right. So is that clear to you? K nearest neighbor, it's a very simple form of classifier. Am I clear? Yes or no?
Yes, ma'am.
Okay, so basically we are moving towards next classifier, that is naive Bayes. So I have given you a situation where I have said that we have to calculate the probability of class 1 given x, class 2 given x, right? This x, is this a single value? Yes or no? This x is a single value? Yes or no? Give me the answer, yes or no?
Single, yes.
No.
No, ma'am.
X is x1.
Single value.
x2, x3 and so on. It means that this x means data, okay, and this data has many features, and these features are may or may not be independent to each other. It means that, let's say I want to create a classifier that classify a student, whether that student is able to win the cricket match or not. Okay, cricket match hone wala hai, or I want to find out, I want to predict that a particular student will able to win the match or not. So I have some data of that student. So that data may be the past matches he has played, maybe how many matches he has won, maybe how is the health is at present, that particular, what is the performance in the last match. So there are multiple features. Those features can be correlated or may be independent. This naive Bayes say, look, I am a very simple classifier, so don't think about extra things. Take one rule of mathematics, that is assume. What to assume? Assume that feature 1 is not correlated to feature 2. It means that feature 1 and feature 2 are independent. It means, let's say, I have given you an example of cricket match, right? So let's say I have one feature that health, yeah, let's say health of that student in last 5 days, whether it is good or bad, and it is written as bad. Obviously, if the health of that person is not good, then there will be some effect on his innings right now. If he is playing his innings, then obviously these are correlated, these are not independent. But this naive Bayes say, no, don't think about it anything. All the features in the data sets, let us assume that all are independent, because if all the, let me tell you what this independence actually mean here is, because when we want to find out this probability, okay, A given B, okay, and this A and B are independent to each other, then it means it is the probability of A into, sorry, I have, so if I want to find the probability of A intersection B, it means that the happening of A and happening of B together, intersection means and. So, and if both of them are independent, it means that it is equal to probability of A into probability of B. It is very simple. And now you will ask, what is the, how this comes into picture? Then there is another formula that I am showing you here. Actually, this was the original Bayes formula that we started learning when we learn about probability in very junior classes. So probability of A given B is equal to probability of A intersection B, probability of B. Okay, so and this intersection comes here. So it means that because this X is the combination of multiple attributes, if these attributes comes together, it means their probability of intersection comes together. And if I am saying that x1 is independent of x2 is independent of x3, then their intersection is the simple product of their individual probabilities. That's why this classifier is called as naive Bayes, because Bayes don't say that the features are independent, but this naive approach say that let us assume this x1, x2, x3 till xn all are independent. So if you want to take the probability of their intersection, please take the product of their individual probability, that's it. So it is written like this. So this is like C given X. This is probability of C given X, and X is number of features x1, x2, x3. So it is equal to just the numerator part, X given C, this X given C into C, right? So this X is a multiple, these are multiple x1, x2, x3, and if I am saying that all these are independent, that's why we take a product. Otherwise, we have a big rule. So that rule, we will be learning it in the next topic today in Bayesian network. So here your problem is solved. You don't have to do anything. Take these xi features as independent and calculate the probability by taking the product. Okay. So let's have some example. So here example is written to you. Consider spam classification. So it means classification there are two classes, spam yes or spam no. So spam or no spam based on the words in email. So there is a email, you have to classify it as spam or no spam. So what's in the email? It's a sequence of words. So these words are the feature. Okay, so if the presence of words free, win and prize contribute to the spam likelihood. So what? According to this formula, I want to find out if these words are there, free, win, prize is there. If X is given, what is the probability of spam? So it is equal to the probability of spam, that is the probability of C, multiplied by the product of individual probability. Means reciprocate कर दो इसे. Right? So spam पीछे चला जाएगा, X आगे आ जाएगा. Spam पीछे चला गया, here, here and here. And I am saying 3 words are there. So what is the probability of free? What is the probability of win? What is the probability of prize? And I am taking the product here. I am not using it in any combination. So it may be they are written in free win prize or prize win free. I am not using this thing. So I am just taking these words are independent to each other, and that's why we will just take the product of probabilities. But in actual sense, these words are not independent. So if you are writing an email and you have frame one sentence, let us suppose that I have written some email to my supervisor, respected sir, please find the attachment of the this written document. Okay, so after this written document, then obviously some words are predictable. Maybe I'm asking for the feedback, so please give me your feedback for that, or he has already asked me to give me this feedback, so I'm going to write it is like, as you said, this PDF is given to you, please let me know if you need anything else. So I can't write unexpectedly anything, right? So things are things are dependent to each other. Obviously your actions are dependent to at this particular state. So if I ask you, let's say you are presently you are listening to me, right? So unknowingly, knowingly, you can't have any action in the whole word in the next second. Obviously you are sitting in front of a screen, whether in the phone or in the laptop. If you want to have there are some subset of actions you can perform. You can either drink water, or you can eat something, or you can say, oh, I just don't have to listen what she is teaching. You just close the flap of your laptop and go. So but there are multiple actions which you can't perform, right? So it means that at which state you are, your state is dependent somehow, or your actions are dependent on the present state. So, but this naive based assumption is, this is the basic assumption that naive say that we don't have any assumptions, so let it be. So that's why it's a simple rule. So let's see one example. So this is example. So these are the 3 words. Same examples, I have framed it in the form of a table. Okay. So these are 3 words: free, win and money. So this is your x1, this is your x2, and this is your x3, and this is your classifier, yes or no. So C1 and C2. Okay. Now what I want to find out? I want to find out C1 given x. Okay. And it is equal to, it is proportional to P of C1 into P of x1 given C1, P of x2 given C1, and P of x3 given C1. So this is the probability. So how you can simply calculate this? First of all, you have to calculate this P of C1. Okay, I am talking about C1 and C2 both. That's why I will be giving you the equations and solving it for both the classes, C1 and C2. So first of all, you need the probability of spam, that is I have given at C1 and C2. So it's more like that simply from here. There are 4 instances, 2 are yes, 2 are no. So 2 by 4 here, 2 by 4 here. Simple. Okay. Next thing is we have to calculate the likelihood. x1 given c1, x1 given c2, like that. So given c1 means, just think about it, c1 is given, it means from these two rows only. From these two rows, how many are x1? Both are x1. So it means 2 by 2. 2 by 2. Okay. Next is from these C1 in these two rows, how many are win? Only one is win. So 1 by 2. It is 1 by 2. Similarly, we will be calculating for others also. Just let me know if this is clear to you. Let me just this. Maybe you are able to see the whole picture now. Just think about it. We have to calculate. What we have to calculate? We have to calculate C1 given x and C2 given x. If this is greater, we will choose C1. If this is greater, we will choose C2. Okay. So for this, we have this formula. So we are just calculating these formula terms. So if there is any doubt, then let me know.
So, ma'am, is the given table serving as the training data?
Yes,
Warrior?
yes, true. So if there is any doubt in any step, then let me know.
No, ma'am. All clear.
Okay, thanks.
Yes, ma'am.
So next is we have to classify a new email. So for new email, what I find, look, this was what training, okay. So now the fifth, I want to say that, let's say I have an email in which two words are there, free and money is there, but no win. It means free win and money. It means x1 is yes, free x2 is no, and x3 is yes, because your x1 x2 is free win and money. So here you are saying free and money is there but no win. So what I am going to say, I have to calculate the probability like this: spam given data, spam not spam given data. So similarly I will calculate, I have actually calculated the probability, I'll just use it here, that's it. Okay, so what is the probability of this thing is equal to spam, P of free given is spam, P of money given is spam. You have already find these probabilities from the training data. Similarly, we have calculated the probability for not spam. So you can see the spam probability is 0.25 and not spam probability is 0. It means that we will choose this data point as spam. Okay, so this is actually the case where you can, use this knife based approach. So why knife based? This is very easy to calculate these things. Okay, so this is simple knife based approach. Is there any doubt here?
No, ma'am.
Okay, so this is simple approach. Now we are going towards advantage, disadvantage, you can go towards it. I am going towards a more generalized approach, because naive based has very strong assumption, which I told you already that this is not the case in real world. So we come towards a more sophisticated or generalized approach, that is called Bayesian belief networks, or you can say belief networks, or you can say Bayesian networks. Anything can be any term can be used. So this is more like a probabilistic or graphical model. Basically it is not graphical model, but we use graphs to represent these states, and this graph is directed acyclic graph, that is called DAG. Okay, it means in this graph the cycle will not be present. So there will be one path that will be not in a circular loop. Okay, why it is important? Because it is basically used in uncertainty, fairness, or these type of presently after having so much in AI, where the fake things comes into picture, where biases are more there, fairness is not there. So this type of belief networks are, because these are based on probabilistic approach, which is properly mathematical, and this gives us a strong point or observation if we are getting any output from them. So it is very important in reasoning. It reduces computational complexity at much way, and generally it is used for diagnostics and decision making. These are generally used for reinforcement learning also. Okay, so let's have what are these. So first thing is, because I told you these are the Bayesian probability based approaches, because it has Bayes and it has network, it means it is a tree like structure, and tree is also acyclic. So directed acyclic, directed means if the arrow is written here, this arrow is different from this. You can't say that these both are same arrows. Okay, so the components are, obviously the tree has some components. First is node and edges. So these are the basic components. Nodes means random variables. It means x1, x2, the features. Okay, and edges means dependency. It means if x1 is dependent on x2 or not, if x3 is dependent on x2 or not, it means it's like that. Okay, how to calculate this, how to get this, we'll discuss it. So एक example है, think about this, कि let there are 3 events. First is rain, second is traffic, third is late for work. Okay, so it is more like late for work is because of rain and because of traffic. It means traffic and rain gives late for work. It means this, in other way, if in dependent form I will say that late for work is dependent on 2 attributes, whether it is rain or traffic. Okay, so it means the arrows are in this form. Just see, observe how the arrows, it means the arrow side is on the dependent attribute, right? And these are independent, so no arrow side is there. So this is a Bayesian belief network in which some nodes are there, which is giving you the information of random variables like features, and these arrows will gives you the information which attribute are dependent on which. So here we can say that late work is dependent on rain and traffic both. Is that clear to you? Here is any doubt?
No.
Okay, now second thing I told you right now just before, ki the probability of A intersection B, this is called joint probability, because A intersection means and we can write also like that, P A comma B. So either you are writing P A intersection B, P A comma B, it's equal. Okay, and it is called joint probability. Joint means those 2 events are happening all together, एक साथ हो रहे हैं. Let's say I am telling you, I am asking you what is the probability that the weather will be sunny and rainy. It means there will be some rain and the sun is also in the sky. So it means you have to think about the circumstances where the rain is also there and the sun is also there. So it means both joint probability. For that joint probability, you can't say that the scenario where the sun is there but not rain. No, this is not the scenario. Okay? So here also I have written this joint probability in the form of attributes. Let's say there are n attributes, x1, x2, x3, xn. Now, because we can't make every combination what there is a process of Markov. Markov means they said everything happens in a sequence. एक साथ नहीं होती है, एक करके होती है. Okay, कैसे? Let's say this is your first variable. When it comes, no one comes. So it's more like the joint probability is because it has comes first, P of x1, simple. Now x2 has come. When x2 come, x1 is already there. So that's why the probability include x2 given x1, right? Now when x3 come, then obviously x1 and x2 were present. X1 and x2 were present, then what is the probability of x3? It means in a sequence we are propagating our network. In a sequence we are calculating the probability. So what I am doing is, let's say there is a ball, there is a bag in which there are n balls and I pick one ball. That ball is blue. So this is your x1. Now next ball will be red. So it's not like that what is the probability of taking out red? No. The probability of red if already one blue is taken out. Okay. Third is what is the probability of green if one red and one blue is taken out. Are you getting my point? Ki how I am getting this joint probability from multiple variables. Is that clear? So is this formula clear to you, this one? It's a simple formula of joint probability where we are just picking one after another and another. Good to go? Can we go ahead?
Yes, ma'am.
Okay. Now, this is the generalized rule. Okay, this is general formula. If, let's say you all have done mathematics, right? So if there is a big formula, right, and if there are some variables inside it at 0, what you do is that in the next step you simplify that equation. Here also I am telling you, let's say I have some predefined information of some variable. For example, I have kept it here as which is highlighted, this one. If I have the information that x3 is not dependent on x2, it means it doesn't matter what you have at the x2, x3 is just dependent on x1. So what I will do, I will remove this. If this is not in the dependent case, then we will remove it from the given condition. For example, let's say मैं आपको बोलूं what is the probability of there are two games of card and this. Let's say you are playing two games. One is of cards, that's वो आपके Uno cards, let's say, and second is you are playing Ludo. Okay, so what is the probability that you are throwing a die and getting 6, and in the Uno card you are playing two games right now, and what is the probability of getting the skip card in the Uno cards in your hand? You will say, ma'am, both those things are very different. It doesn't have any dependence on each other. Okay, it's not like that if I have skip in my hand and I'll throw it and I will get some number. No, there is no dependence on them. So it means that the joint probability will be the product of these two, because I am using and there, right? Similarly, if I say what is the probability, if just think about it, I am going towards the conditional probabilities. I am telling you what is the probability that die has 6 given you have the skip card. Now you have skip card in your hand. What is the probability you will have 6 on your die? You will say, what is the relation between these two things? It doesn't matter whether it is a skip or not. It is equal to 1 by 6. It means it is the probability of 6 only. So that's why if some event is written at the given condition and this event is independent of that, we remove the given condition. So similarly here also x3, I am telling you, have some previous information that x3 is not dependent on x2, it is dependent only on x1. That's why we remove the x2 and we simplified the equation. So in this form, we can say that using this big rule, if we have the information of some variables, we can incorporate it and remove the redundant terms. How you can do that? Just think about this. This one. So these are the dependency relation that I know from some previous, previously, or I know in hand that x1 is dependent on, there are, look, how many variables are there? x1, x2, x3, x4, x5, x6, x7, there are 7 variables. And I have this information that x1 only depends on x2 and x3, x3 only depends on x3 and x7, x4 depend on x5, x6 depend on x7, x2 depend on x4, और बाकी बचे हुए बाकी सारे independent हैं. Okay, so how you are going to represent it using graph, first thing, and secondly how you are going to put it into the formula. So just think about it. First let's see the graph. So first is your x1 is dependent on x2 and x3. So let's make the graph here. So x1 dependent on x2 and x3. So arrow will be down because it is dependent. Now x3 depends on 6 and 7. So x6 and x7 then it is this one. x4 depend on x5, x4 अभी आया ही नहीं है तो x4 देखते हैं बाद में, ये वाला बचता है अभी. x6 depend on x7, so there will be a arrow like this. x2 depend on x4, so x2 is dependent on x4, and last one is x4 is dependent on x5. So this is the graph actually. So if I give you these conditions, can you make the graph? Yes or no? If I give you these type of conditions, can you create one Bayesian network? Yes or no?
Yes. Yes.
Yes, ma'am.
Yes.
Very good, very good. So now look, this is the Bayesian network. Okay, this network, if you see this network, acha, just let me know if I write you these dependence or I give you this graph, which is more convenient to see or get an idea of the whole system. Should I write to you these depend on, or should I give you the graph?
Graph.
Graph,
Graph.
right? That's why we build this graph from the equations or from the circumstances that we know previously. Now think about the mathematical equation. So mathematical equation, this is the same formula that we have used previously. x1, x2 given x1, x3 given x1 comma x2. Look how the things are building up. Okay, I have this graph and I know x1 is dependent on x2 and x3. So I change this p of x1 to this equation. x1 given x2, x3. x2 is given dependent on x4. So that's why I have written write x4 in the given condition with x2. Similarly, I change x3, I change x4, x5 is not dependent on anyone and x7 is not dependent on anyone. That's why these are chosen like this. So look how this big formula is changed into this picture. So this is how, using these dependency relations, we can have some idea and we can remove some redundancy, plus we can have some idea of the system as well. So this will help us to find the more accurate, more real-time solution rather than those naive conditions. Okay, so this is the first thing. Now confusing things comes into picture right now. I give you one independence situation. Independence means two events are completely independent to each other. That is called independence. It means for independence, P of AB is equal to P of A, P of B. And if AB are independent, then P of A given B will be equal to P of A simply. Because given condition में independence मैंने हटा दिया. There is another term, conditional independence. Sometimes some events are there which are not independent to each other, but given some condition they become independent. For example, let's say, how I'll take the example. Okay, there is these three things. Example is given here: rain, wet grass, and sprinkler. Okay, so this wet grass and sprinkler is may be dependent on each other. If I tell you only two things, the grass is wet and there is a sprinkler, so what you will say that obviously the the wet grass is wet because of this sprinkler. There is high chances. It means these are both connected to each other. Okay, but if I say that already the rain has happened, okay, what is the probability of wet grass by sprinkler? So you will say it doesn't matter whether the sprinkler is open or not. You have given me the condition that it has already rained. So if it has rained, then obviously the grass will be wet. So that's how, given this condition rain, these two become independent of each other. It doesn't matter whether a sprinkler is there or not, the grass will be always be wet. Okay, so this is how this term is called as conditional independence. It means given some condition, now two events are independent. So what you write it as here, same, this is changed to P of A given B, B given C is equal to, just that this C has comes into picture. It is P of A given C, P of B given C. So it means that now this given condition is that important for independence. Without this, we will not be saying this is the only product rule. ये simple product rule नहीं होता. If you are saying like this, so it is more like what if it is not conditionally independent, then how you have to write it out? P of A, comma B, comma C, given of P of C. So this is different from this. Okay, so now I am saying given C, some things are independent, that it means that you can go in this product rule. So this conditional independence is very important, that how many nodes in your graph are conditionally independent. So for that there is a thing like D-separation, and it is very important. D-separation means it's a method used in Bayesian network to determine whether two variables are independent given some observed evidence or not. It means that, let's say there are 3 nodes, this one. So I want to say this A node and B node are independent on this node. Okay, so it means that there will be 3 someone asked some.
Yes, ma'am, this side, Renuka.
Yes, go on.
Ma'am, the previous slide, I don't know, I was confused. I'm not able to understand. Yes, conditional independence. Can you please repeat it?
Okay,
Sorry.
okay, there, no, it's okay, it's all right. Think about it, there is a concept of independence. Independence means two events are independent of each other, means it doesn't matter one happens or not happen. Okay, so let's say two events are playing cards, having if you are playing cards, having a card of skip or having a card of queen in your hand, and second is getting 6 on a die. Okay, so these two events are completely independent to each other. It doesn't matter, those don't link with each other. So using the independence rule, there are two things. First is joint probability, which is like this. If the joint probability of two events which are independent, it is equal to the product of them. It doesn't matter, okay. If they are in the conditional form, then obviously the conditioned statement is removed, because A is not dependent on B, so that's why this conditional probability is equal to the probability of A itself. Is that clear? Is this thing clear to you? In simple independence, I'm not talking about conditional right now.
Yes, ma'am.
Okay, so now, just if these two are not independent, then P of A into B will be actually equal to P of A given B into P of B. This is the actual formula, but because this became like this, that's why we can write like this. Okay, so ultimately what I wanted to tell you is, if two events are completely independent to each other, then their conditional probability means nothing. It's the same probability as you are asking. Okay, वही वाली चीज़ है, आप मुझसे बोलोगे कि I am teaching you something and India is playing the match, that what is the probability of India winning the match if I am teaching? So you will say कि ma'am, it doesn't matter whether you teach or not, they will play their game, right? So it doesn't matter. But some events are not independent. For example, let's say there are two things. The grass is wet and the sprinkler is there. Sprinkler means this is a device, right? A tap like device which has some fountain like structure which sprinkles water on the grass. Okay. If I tell you these two things, it means they are dependent on each other, because if sprinkler is open, the grass will be wet. If the sprinkler is not open, then maybe the grass is not wet. So it means that these two things are dependent on each other. So if I say what is the probability of grass is wet if the sprinkler is there, okay, what is the probability of grass is wet if sprinkler is not there? So there means there will be some probability given statement. Given statement is very necessary. But now I give you one event, rain. I give you this information. Let's say rain has already happened. If rain has already happened, what is the probability of grass is wet given a sprinkler? You will ask me, ma'am, what is the need of sprinkler? Na? You already told us that the rain already happened. So whether there will be sprinkler or not, the grass will be wet, obviously. Okay, so that's why we can say that this event grass, wet grass and sprinkler become independent if I know the information of rain. दूसरे सेंस में मैं अगर बात करूं, if I have the information that sprinkler is opened on the grass, then it doesn't matter whether it rains or not. It means that on some given statement, the two events become independent. This is called conditional independence. So in this way, we can use the same formula but on conditional conditions. So probability of A, B given C, if this A and if after having this C, this A and B become independent, then they are called as conditionally independent. And now I can write simply probability of A given C, probability of B given C, because these two events, let's say these are E and F. So it means like you are saying the probability of EF is equal to E and F. It's more like that. Is it now clear to you somehow?
Yes, ma'am. Thank you so much.
Okay. So next thing is we have to find out that where this conditional independence is there. So that's called as D-separation. So there are some rules. Okay, let's go with definition, then we go towards the rules. Definition is two variables x and y are D-separated, are called D-separated. Two variables means two nodes. This is x and this is y. D-separated, or we can say that these are conditionally independent. Obviously two variables are conditionally independent, there will be some condition given to it. So what is this condition? On observed variables z, there are some variables z in between. If all the path between x and y are blocked by z, so if there are some paths between x and y and all paths can be blocked by z, then it means that given z, x and y are independent. Why? Because look, all the path having this z in common. It means that if we know the information of z, okay, then you can easily get this information of y and you can easily get the information of x. It doesn't matter what is x, what is y, you know the intermediate thing. It's more like you have started with the journey, okay, you have an end point and a start point at the end point, okay, and if you know something in between the journey, you can have an idea of start and the end. So it means that it doesn't matter what is in the start, what is in the end, but using this intermediate information, you can have the idea of both. So it's more like that thing. So I am going to give you some definitions again and will give you a trick also so that you can remember it. Okay. So basically two things are there. First is there are three nodes x, y and z. Second thing, there is a path between them. It means there is a path between x and y in which there is z between them somehow. So there can be multiple ways in which z is connected. So z can be connected as simple, either like this or like this. Okay, so this is called chain structure. Second observation can be z is like this. This is called fork structure. And third is collider. It means z is in between and both arrows are coming here. So this is collider structure. Now for each these structure, these three structure, we will say if z is given or z is not given, what will happen. Okay, so there will be two things: observed, not observed, observed, not observed, or observed, not observed. Second thing is they give the information whether it blocked the path or not blocked the path. So block means, always remember, block means independent. Blocked means independent and not block means dependent. So if these conditions are met, then we can say that z is x and y are conditionally independent on z. So there is a graph you will get in that graph I'll say any two nodes, let's say x and y, and I'll say whether this x and y are independent, conditionally independent on z. So you will check first these three structures, second if z is observed or not observed, whether the path become independent or not. How? Let's see some examples. So first structure is chain structure. Okay, so let's say the observation is if z is observed, it means x and y are independent. If it is not observed, then it is dependent. How? Let's see one example. So there are three things, nodes x, y and z. X means rain, z means wet roads, y means traffic jam. Okay, and this is the example of chain structure. It means only one way is there. It means z is in between and this is more like this. Okay, so graph representation is more like traffic jam is dependent on wet roads, wet road is dependent on rain. It means rain hogi to obviously roads will be wet, and wet roads hongi to traffic will be jammed. Okay, so this is z, this is x, and this is y. This is more like that. Now question is, we have to think about this observed and not observed. Observed, let's go for not observed. Not observed means dependent. Not observed. Not observed means, let's say we don't know the information whether the roads are wet or not. Okay, we don't have this information. You have rain or traffic jam. So is rain or traffic jam are dependent on each other? Yes or no? Just think about it. We don't have the information of wet roads. Are the rain and traffic jam dependent on each other? Yes or no? एक के होने से दूसरे पे फर्क पड़ेगा या फिर कुछ भी नहीं पड़ेगा? Let me know, yes or no.
पढ़ सकता है.
पढ़ सकता है.
Ma'am. Yes.
It means they are dependent. So it means this observation is correct. This rule is good. Next rule is with observed. Okay, this is not observed. Let's say I am telling you the roads are already wet. Okay, now rain and traffic jam are they dependent? जब मैंने आपको बता ही दिया कि the roads are already wet, it means that there will be some traffic jam. Whether it will rain or not, it doesn't matter. Or this is right. So it means rain and traffic jam will become independent if we have the information that you have wet roads. Okay, if this observation is given to you, if there are no wet roads, obviously, ठीक है, it means अगर wet roads है नहीं, it means there will be no rain. Rain हो ही नहीं होगी तो traffic jam भी नहीं हुआ होगा. It means that having this, this information of this variable, these two variables become independent. So in this rule, we can say that this rain and traffic jam are conditionally independent on this. It means if it is given to you, then they are independent, and if it is not given to you, then they become dependent. It's a simple case. Okay, so this is example of chain rule, chain structure actually. Next structure is fork structure. So fork structure is if observed then block, if not observed then does not block. It is same as the previous one. Look, if observed block, not observed not block. So these have the two rules which are same in both the structures, fork and chain. Let's see example once again. X is sport popularity, Z is cricket match, and Y is stadium crowd. So now this is the fork structure. Fork structure means the between one there are separations. This Z is this, X is this, and Y is this. Okay, so from the cricket match, it means sport popularity and stadium crowd is dependent on cricket match. Okay, so now first is not observed. Let's say not observed means it should be not blocked. Not blocked means dependent. So not observed, let's say I have no information of cricket match. Okay, so sports popularity and stadium crowd will be dependent. Obviously, if the sport is more popular, then stadium crowd will be more. So these are properly dependent to each other. It means second rule is satisfied. First rule is, let's say I gave you an information of cricket match. Okay, so if I have the information that there is a cricket match, then obviously the stadium crowd is more. because it is directly dependent on this. So it doesn't matter what is the sports popularity. I am telling you that from this cricket match the stadium crowd is this, then it doesn't matter what's the sports popularity or not. Okay, so it means it become independent. So these two rules makes this sports popularity and stadium crowd become independent of this cricket match having this folk structure. Is that clear? Are you able to grasp it ki what I am trying to tell you? So these are the
Yes.
rules
Yeah.
that they have created properly, but it's just like we have to just sometimes when we ask about these rules we forget these rules. So there are three structure. In two structure, this fork and chain, the observations are same. It means not observed, not blocked, observed, blocked. Block means independent. You have to think about it, but you have to just make sure block means independent. Next is this collider structure. This is, you have to pay attention. Here the roles are reversed, means not observed means blocked or observed means unblocked. And here the observed is not just for Z, it means any of its descendants. It means if Z is here, it means any of let's say P, let's say P, all this can be happen. Z or any of these descendants are observed, then path is unblocked. Let's see one example. Rain, wet shoes and sprinkles, again the same examples, and this collider means this one, like this. So if it is not observed, not observed means here the thing is opposite, it will be blocked, it will be independent. So if it is not observed, then they will become independent. Okay, wet shoes is not given to you, rain and sprinkles are two different things, it doesn't matter to them, so they are become independent. But if it is known, if you know that the shoes are wet, then obviously you can have an idea the shoe, if we observe that wet shoes are there, then knowing that it doesn't rain, it makes the more probable chance that sprinkler will be having on the shoes. It means that wet shoes is here and it is dependent on two things. So if I know this, okay, if I know this and I know that this is dependent on A and B, and I know A is somehow low and this is high, you will get the third variable as obviously this will be high. So this become dependent to each other. All right, so in this three case what I am going to tell you is want to tell you is that this wet is dependent on A and B, and you know the value of wet, and if you know the value of A, then obviously you will have some idea of B also. So it means that B is dependent on A if you know the value of wet. If A is low, B is more, or sometimes some relationship will be there. So in this way, these three structure will help you find out that which two nodes are independent, conditionally independent of which node. So these are the three things. Just I have actually summarized it into a table also. You can have it, observe it properly. When you will observe it, you will see some examples. You will get to know very clearly. Okay. So I want to actually, are actually very theoretical, so I want to give you some example first. Okay, theoretical question I'll not deal with it. I have one question which I like it. Okay, this thing, just
Ma'am, how many more minutes will the class continue?
10 minutes. Okay, just let me know which of these are correct from this Bayesian network.
Option C.
Sorry?
Option C.
C. Any other choice?
A only. A only.
Just let me know how E is causing D. The arrow is
A
not
alone.
like this, right? So the answer is A only. Wait. Oh, correct. Sorry. A is also not the answer. Why? Because A and C both are causing D, so you can't write A cause D only. Okay, so you have to write A comma C. You have to write A comma C causes D. You can't write A causes D only. Is that clear to you? So it means if you are writing it into the form in a statement, and if two variables are helping out for the two combinations are going to give you some variable, write it in a single sentence. Okay.
Ma'am, I have a question. When multiple variables parallelly causes some other random variable, then we have to include all of these.
Means like A and C is causing D, right?
Yeah, exactly.
These are
Yes.
not parallelly, these are combinedly. These are combined together. Okay, so because these are combined, that's why they have to written A comma C, because just think about it. If you are not going to, if I just read out this sentence, it means that A is causing D. So using this, I can have some inference in my mind. Okay, so that's why I can just write A comma C cause D. It means both of the combination is giving us D. First thing that this I wanted you to know. All right. So that's why none of the above is the answer, because node D is dependent on both A and C. So it's not like that A causes D is not, it is incomplete information, I can say. Okay, so this is incomplete. Second is this. I want to tell you the same graph is there. Okay, now question is which of these are correct. So first is D is independent of B when C is known. So there are three variables used here, D, B and C. So D is here, B is here and C is here. Okay, so this is the fork structure, right? ऐसे जा रहे हैं आपके, और इसमें था कि अगर C आपको known होगा, if C is known, then it will block the path, it will independent. So it is true. Any doubt in this statement?
No,
That's why I
ma'am.
have written it
Okay.
here, fork to A. Okay. Second is A is independent of C when E is known. So A is here, E is here, and it has, sorry, A and C, this A and C is given, and this is like a collider, right? Collider means here. But you will say, ma'am, collider is not at E, it is at D. So that's why there is a statement there, D and its descendants. So it means I'll convert it into a single path. Okay, so it means that in collider, what is written, if this is observed, then it will not block the path. If it is observed, then it will become dependent. So it is known, it is not independent, it will be dependent. So this is wrong. That's why I have highlighted as red. It is not correct. Is that clear to you? Second statement. Is it clear, yes or no? Second statement.
Ma'am, bit
Again,
confusing, ma'am. Yeah.
just
No.
look, there are three nodes A, C and E. A is here, C is here and E is here. Okay, and I always tell you there is a path between A and C. So the path between A, C and E, we have this node also, right? So this
Yes,
node
ma'am.
is having a structure of this, like collider. Collider is the third structure in which the rule was opposite. Collider में आपका था observed means no block and not observed means block. ऐसा था आपका रूल. Okay, so अगर it is observed, so it is no blocked. It is not blocked, it means it should be dependent. Not block मतलब block का मतलब independent का था ना, no block मतलब dependent. If this is observed, then they are dependent, no block. So they are dependent, here it is written as independent. That's why this statement is wrong.
So ma'am, here observed means known. E is known.
Yes.
Okay.
Okay, got it?
Okay.
Now next is A, B and E. We will be talking about this. Let me change the pen. Talking about this A, B and E. Now there is no common path between these three, because A, D and E has separate path, C, B has separate path. So from the above you can say that if this A, B and E, from the above, A and C are dependent, A and C are dependent if E is known. Okay, from this statement, from this very statement, if E is known, then A is dependent on C. This will be dependent. Okay, if these will be dependent, and obviously this B is dependent on C, then obviously it will be dependent on A. Getting my point? Just think about it. There is no common path between A and B, but from the previous statement, what I wanted to say is B depends on C. Is that clear? Yes or no? B depends
Yes,
on
ma'am.
C. ठीक है? I have to find out if B is dependent on C, is C is dependent on A or not. I have to just think about it. Because if this is dependent on C and C is dependent on A, then obviously these both will be dependent. Okay, so C will be dependent on A if E is known. It can be seen from this statement because it was wrong written. So from this statement we can see that if E is known, A and C are dependent on each other, and B obviously depend on C, so it will depend on A also. Is that clear? So this statement is written as independent, that's why it is also wrong. Good to go?
Yes, ma'am.
Okay, now think about it. I am telling you B is dependent on C and C is dependent on A if E is known. Now D portion is A, B and C. A, B and C, right? These three things. Knowing that C, D, B are independent, C, D, B are independent, given that C, okay, just think about it like this. Here C is known, it means this is known. If this is known, then which two nodes are independent? Just let me know. If this is known from the first statement, we can say D and B are independent. Yes or no? When C is known, D and B are independent. Okay, when D and B are independent, obviously, and D depends on A, then obviously A and B will be independent also. Getting my point or not? Here the statement is written as when C is known, what is the status of A and B? So when C is known, I don't know the status of A and B, but there is a joining node D here. So when C is known, I can say D and B are independent. These two are independent. If these two are independent and this depend on A, this does not depend on any other thing, and B does not affect D, then obviously B does not affect A also. It's so true.
Got
Any
it,
doubt
ma'am.
here? Got it? So
Yes, ma'am. But all three things make some bit confusion. No, but yeah.
yeah,
Yes.
means I mean when you just think about it, that's why I have written all these things in small hints, and I wanted to solve these two questions especially in the class. That's why I have given this type of explanation. So just go back home and read all these slides. Now you will have an idea that how things are going on. Okay.
Yeah, sure, ma'am.
because this Bayesian network, some part of it we will be covering in the next week also. Okay, if we have some more questions there, then I'll keep it. And the last, this topic, multi-class classification, is very easy. It's a theoretical concept. You can go through the slides, you can have a simple answer. Okay, you can have an idea that what are these. It's a simple thing. Multi-class, it's not a big thing. Still, if you have any doubt, we can cover it later also. So this is all about week 8, especially this Bayesian classification or Bayesian network. You have to be careful about. Okay. So if you have any doubts, then go ahead and just give me the feedback here.
Can you share the PPT?
Yeah, this PDFs will be uploaded by in next 15 to 10 minutes. Where all the PPTs are
Okay.
there, this PPT will be there also.
Thank you.
Okay, so any other doubt?
No, ma'am.
All right, thank you so much.
Thank you, ma'am.
Thank you.
Take much efforts. This can be the best explanation for this topic.
Sorry?
This can be the best explanation for these topics.
Yeah, means if you can, means when we also go through these rules, we don't remember this. Sometimes it's very
Yes.
confusing also. So these are not you just have to actually calculate the probabilities, and generally when situation is given to you, some things are more clear. That's why
Yes,
if you
ma'am.
know this rule, then it will be more helpful. Secondly, it's not like that if you are saying, if you have some probability rule and you just miss this part that, oh, these two events are conditionally independent or dependent. It doesn't matter, because when you solve those equations, you will get simplified. You will get the same answer. It's more like that.
Okay.
And probability is actually a big topic. So the more you can practice it, you can have an idea at how to go towards it.
Yes, ma'am. Thank you.
Okay. Thank you so much.
Okay,
Then with
thank you,
this,
ma'am. Good night, ma'am.
Thank you, ma'am.
yes, any doubt?
Thank you.
Okay, thank you so much, and we'll meet the next week, same time. Okay, bye bye.
Thank you, ma'am.
Bye.